Hi class, Ms. Cornacchione here. This video is on topic C4 and it's on power and efficiency. So these are really important topics when we're talking about energy, which is the unit that we're on. So let's talk about power. Power is the rate at which work is done. So when anything is a rate, it's divided by time. So how much work is done in how much time, how quickly is work done. So we've got power. Work is units of joules and time is units of seconds if you're talking about SI units. So joules per seconds gives you watts. And power is a scalar quantity because work and time are scalar quantities. So we said 1 watt is 1 joule. Those are units of work divided by units of time, seconds. So joules per second is a watt. So that means a 60 watt light bulb uses 60 joules in 1 second. There's also a very common unit of power, horsepower. 1 horsepower is equal to 746 watts. So if we take a look at that power equation again, so power is the rate at which work is done. Power is work over time, but there are several ways of calculating work. So we do know that work is equal to the change in energy. So any way that we can calculate the change in energy in joules, that could be subbed into the numerator. So yeah, the change in energy in joules can be subbed into the numerator. The change in time could be subbed in seconds. So that's one way to calculate that the power. But we also know that work is F cos theta D. So that's the force times cosine theta, where theta is the angle between F and D, times D, displacement. So you've got force times displacement times cosine of the angle in between the two. Could give you the numerator, divided by time. Power questions are not at all difficult if you look at the equation. It's just work over time. But sometimes if we make a mistake with them, we just don't quite know how to find work. So I encourage you to really practice these questions, because when you're practicing a power question, power is probably part C, and part A and B were some sort of energy question from what we've learned so far. So if you're practicing a power question, you're practicing a whole bunch of other things in the scaffolding of the question. So let's try an example. Calculate the power of an athlete if they transform 3.6 kilojoules of chemical energy into kinetic energy and thermal energy in 15 seconds. So if you imagine, so this person through running is doing an energy transformation. The chemical energy is turning into kinetic energy and thermal energy. So let's just think about that for a second. When you're burning calories, it's basically combustion in your body. You're taking those high energy molecules and you are breaking the bonds. So you're breaking the stored energy within the bonds of the nutrients within the food. And that's the source of the energy. So when they say eat breakfast, it's the most important of the day, most important meal of the day, it's fuel, it gives you energy. So there is a scientific interpretation of that. Food does give you energy because food gives you the nutrients. Nutrients are the molecules which contain the chemical bonds that when through metabolism, through burning that fuel, you are releasing the chemical energy stored in those bonds. And then what do we get out of it? So what is having energy in terms of being like an athlete? So you're running, you have speed, so there's kinetic energy, and you also warm up when you're doing that, so there's thermal energy. So what goes into, if we were to draw this energy transformation like a box, what goes in and what comes out? What goes in is the chemical potential energy, and what comes out of it is mainly kinetic energy and a little bit of heat as well. So we're given the time, we're given the energy. Notice the energy or the work or the change in energy is not SI units, it's kilojoules. So we have to change that into joules before we get started. So delta E is 3,600 joules, time is 15 seconds. Our power is just 3,600 divided by 15 seconds, and we get a power of 240 watts. So watt is the SI unit, that we get when we divide the SI units of energy and time. So the power delivered by the athlete is 240 watts. Let's try another example. A 65 kilogram physics student rushes up a flight of stairs 3.8 meters high in 4 seconds. How much power is developed in watts and in horsepowers? Okay, so first of all, power is the change in energy over time. Do we have time? Yes, it's given us 4 seconds. Do we have change in energy? Not directly, but we do have enough information to calculate the gain in gravitational potential. And there is an assumption here that we don't gain kinetic energy. So it's tiring going up the stairs. You're going to go up the stairs. It says rushing, but you're going to go up at a steady speed. So there is no change in EK. Of course, there is EK, 1/2 mv squared. There would be a value that we could calculate if we have speed. But there's no increase in kinetic energy anytime you're traveling at constant speed. So let's assume no change in speed. Therefore, all of the delta E is just final EG minus initial EG. Final EG we'll say is at the top, so that's position 2. Initial EG is at the bottom, so those are the 2 points of the energy transformation that we are comparing. And MGH2 minus MGH1 gives us 2,423.07 joules. We sub that into the equation, divide by 4 seconds, and we get 605.767 watts. Converting to horsepower, notice in our previous slide, we had a conversion. 1 horsepower equals 746 watts. If you take this value over that value, that is equivalent to 1 because the numerator is equivalent to the bottom. So we can make use of that conversion factor. And you might wonder, do I use 746 watts divided by 1 horsepower or the reciprocal of that? We want to get rid of watts, so you put watts on the bottom. So it's 705.767 divided by 746. And that's how you put that in your calculator. You see the watts canceling out and you're left with horsepower, 0.812 horsepower. I recommend, we haven't done the unit analysis really showing it in a long time. So just to remind you, you put the number that you start with over here and you write the units that you want to end up with over here. And you're going to multiply by 1 or more conversion factors so that the denominator is canceling with this numerator. And you put something on the top that's equivalent to the bottom. So it could be 1 minute over 60 seconds, or in this case, it would be 1 horsepower divided by 746 watts. And then the final answer would be rounded to 2 significant figures for 610 watts or 0.81 horsepower. Let's do another example. During a physics lab, Jack and Jill ran up a hill. Jack is twice as massive as Jill, yet Jill ascends the same distance in half the time. Who did the most work? Who delivered the most power? So you want to think, how is power related to work? We've got our power equation, which is work over time. We've got work equations, F cos theta D. Work is also the change in energy. So if we have enough information to calculate a change in energy, the difficulty in some physics problems, you might see this as a difficulty, is that there's no numbers. For some people, that makes it a lot easier because you're working with the concepts. For some people, they're very used to having the numbers. So if you really wanted numbers in this problem, why don't you just assume some numbers as long as they fit the rules, and you'll hopefully get the same conclusion as long as you're not picking any special numbers. So let's say if Jack was a little boy that was if Jill was a little girl that was 10 kilograms and Jack was 20 kilograms, because it says Jack is twice as massive as Jill, you could set the distance from the bottom of the hill to the top, and then which would be the same for both of them because they both ascend the same hill, and then half the time. So let's say 10 or 5 seconds versus 10 seconds. So what we do is I'm going to show how to do it without assuming numbers. So we know work is force times displacement. We know it's also change in energy. Since we're talking about the height of a hill, let's use MGH. So for the change in energy for Jack, it's 2 times the MGH of Jill. So work that Jack does is 2 times the work that Jill does. Jack does 2 times more work. But if we look at power, Jill has half of the time. It's half of the time of Jack's time. So 2 times the energy divided by regular time versus energy divided by 1/2 the time. It works out to be the same. 2 times 100 joules divided by 50 seconds versus 100 joules divided by 25 seconds. So it's the same power. Power is the rate that work is done. So our last example is what is the cost of operating a 60-watt light bulb for 4 hours a day for 1 week if the price of electrical energy is 7 cents per kilowatt hour? So one thing to mention is with this power equation, we've been working with SI units, energy of joules and time in seconds. And then joules per second is watt. But we operate appliances in terms of hours. And appliances are rated with kilowatts, not watts. So kilowatt hours, if we multiply power and time, is the unit of energy that is more commonly seen in problems where you're calculating the cost of the electricity. So if the power is 60 watts, we know that's 0.06 kilowatts. Time, 4 hours, 7 days a week, is 28 hours. So 0.06 kilowatts times 28 hours gives us 1.78 kilowatt hours. I decided, you didn't have to do it this way, but since the price per unit of electricity was the kilowatt hours, I decided to turn the power into kilowatts and the time into hours. You could have also figured out what 1 kilowatt hour is in watt seconds. So how many cents is it for 1 watt second? So you could have done it that way as well. But I chose this way, and then I do 8.7 cents for every kilowatt hour, and I have 1.68 of those. So multiplying those together, we get 15 cents. Okay, our last concept is about efficiency. So remember this diagram, we talked about the incandescent light bulb. For every 100 joules coming in, only 5 joules is energy coming out. So an incandescent light bulb from the conservation of energy lesson, it is an example of energy transformation. And most energy transformations, we were really looking at the energy that you put in and the intended energy out, or the useful energy out. We assumed it was 100% in a lot of our examples, but what really happens in real world energy transformations is there's almost always some form of energy that's a wasted form of energy that we don't think to mention. We didn't think to mention in our table. So the primary form of energy coming out of this light bulb is actually thermal energy. We have 95 joules of energy of heat, only 5 joules of energy of light, which is the intended energy. Efficiency is referring to how much good energy do you get out compared to how much energy do you put in. So if you think about I guess there's kind of a metaphor of like if you're, how efficient you are with your, I guess, studying. So let's say if you were to put in 100 minutes into your studying, but what you got out of it was a poor quiz mark. So you did not, it wasn't I don't know, an efficient use of time, or it wasn't how much you put into it versus how much you get out of it. So if you got 100% on your quiz, whatever you put into it, it was really efficient. I don't know if if that was the best example. I didn't plan to talk about that example, but yeah. So how much useful energy do you get out of the energy transformation compared to how much energy went into it? That's what efficiency is talking about. And you'll see a lot of high efficiency labels on appliances. And that's scientifically, that's what that's talking about, is how much energy do you get out of it that's usable energy compared to how much total energy in. So efficiency is a ratio between energy out and energy in. The exact formula is percent efficiency equals E out over E in times 100%. This is sort of more of a definition that we put math to than a formula. So it's sort of just an equation that I decided to say E out and E in. There's going to be two energy values either calculated or floating around in your problem, and you might struggle with knowing what is the energy out and what is the energy in. So one trick is that the larger amount of joules is always the one that goes in the denominator, because you can never be more than 100% efficient. Otherwise, it denies the law of conservation of energy. So E out is the amount of useful energy that you get, and E in is the amount of energy you use. Violates is the word. If this was a more than 100%, it would violate the law of conservation of energy. So maximum efficiency is 100%. That's what's ideal, but in reality, there are losses due to friction, heat, etc. So we already talked about the incandescent light bulb is a very low efficiency. 5 units of energy, so 5 joules divided by 100 joules is only 5%. So this is only 5% efficient. So in an example, we've got a 60 joule a light bulb uses 60 joules of electrical energy each second and produces 9 joules of light energy each second. Calculate the percent efficiency of the light bulb. So we've got energy out is 9 joules, energy in was 60 joules, and that is a percent of 15%. We've got another example. So we've got a golf club being hit with 65 joules of kinetic energy, and the golf ball was stationary. And the golf ball had a mass of 46 grams. The energy transfer is only 20% efficient. Calculate the initial speed of the golf ball. So if it was 100% efficient, which is what we've done in previous problems, you would say there's kinetic energy being transferred from the golf club to the golf ball. So you'd calculate 1/2 mv squared of the golf club at contact, and then that would be the 1/2 mv squared of the golf ball. The masses would be different, so that's why the V's would be different. But we've only got 20% efficiency. So EK goes into this energy transformation process. So I write it as like a black box. Like this is, we don't know how the energy transformation happens, but we know what comes in and what comes out of it. So it's a way to simplify it, the energy transformation. EK comes in for the club, and EK for the golf ball comes out of it, and also maybe some sound, maybe some thermal energy. So there's energy lost or wasted, and there's the useful stuff. You intend to get all the kinetic energy to the golf ball. Our percent efficiency is 20%. We have our equation. So what is energy out and what is energy in? This is the energy in. This is the energy out, because energy out, we don't care about this. We only want to sub in the useful energy. We're going to rearrange this to get energy out and solve for 13 joules. And you might say, well, that's not what was asked. I want the speed of the golf ball. So you want the speed that's associated with this EK. So our first step was to find that EK. And our EK was 13 joules. Then if EK equals 1/2 mv squared, we rearrange to solve for V. And we get 24 meters per second. Okay, so time to do some practice problems. So the first 3 are power and the last 4 are efficiency. There is also just coming up, the next task I'm going to assign to you is a worksheet on comparing different energy method generations. So I just wanted to speak to that now. Since there's not going to be a video for that task, it's just going to be reading the textbook. And so you're going to read about these different methods of energy generation. And you have done this in grade 9, learning about different forms of energy, electrical energy generation. So as you read about each of these in the textbook, I want you to think of what is the energy transformation. So for example, fossil fuels, you're burning chemicals. So it'll be chemical potential energy turns into electrical energy. For solar energy, it would be radiant energy turns into electrical energy. For wind power, it would be the kinetic energy of the blades turning of the wind turbine. So kinetic energy to electrical energy. So you'll notice all of these end up with electrical energy. That's the point of this, is we're comparing ways of generating electrical energy. Then when you read about an advantage, write it down. When you read about a disadvantage, write it down. Don't be so concerned about having like a certain number for each of these. Just take from the textbook. So it's okay if you have a blank. And I just want to give you some tips. Some ways that you could find an advantage or a disadvantage. And I just want to mention this is, there is a lot that goes into a country's decision for how to get their electrical energy. There's political, social, environmental considerations, and this is, and you will probably, even if you don't kind of pursue pure science, you will likely come back to the debate of, you know, what is the method of electrical generation that makes sense to be Ontario's primary method of generation. And certainly as you guys study and enter the workplace, it's going to shift because technology gets better. And if you look country to country, what's best for each country at this moment, or at least in 2017, is different. Canadians use a large amount of energy because of our climate, and it's so damn cold in the winter. We use the furnace for a lot of the year, and then we can, in some parts of Canada, have hot summers where we're using air conditioning as well. So because of Canada's climate, we do have quite a bit of energy that is consumed, that needs to be produced. So this is what it is for Canada in 2017. I want to give you an idea of what are some of the pros and cons. So you have to think, where did that electrical energy come from? It was transformed from a different source of energy. So that source of energy was harnessed from maybe these: wind, water, sunlight, food, oil, coal, or natural gas, or uranium. And there is one con might be that it's not sustainable or it's not renewable. So those mean the same thing for our purposes. A non-renewable energy source, the source is used up faster than it's replaced. So for example, petroleum, natural gas, coal, uranium, that's used in nuclear reactors, propane. So we will run out of these. As opposed to being renewable or sustainable, this might be a pro. Renewable energy is replaced as fast or faster than it is used up. So the sun, we're not going to run out of the sun, the source of energy from the sun, where we likely won't in our lifetime. And other ways that the energy source is renewed, or it doesn't run out. So non-renewable versus renewable sometimes gets confused with being really green in other ways. So greenhouse gas emissions is also a consideration. So if you don't remember from grade 10, the climate change unit, greenhouse gases such as carbon dioxide, methane, so we say like carbon, because carbon dioxide is the biggest one that we're thinking of. Carbon emissions contribute to the climate crisis. In other words, contribute to the anthropogenic, that means man-made greenhouse gas effect and global warming. So that just gives you some idea. This greenhouse gas emissions would be a con, sustainability would be a pro, non-renewability would be a con. So, you know, cost and only available in certain climate would be some other things to look out for. So you're going to fill this out not for today's task, but for the next task. And that'll be clear on the Google Classroom post. So for now, do some practice questions, submit it to Google Classroom, and don't forget to fill out the exit ticket for this lesson.